Okay, so now let's talk about the hormones of the adrenal medulla as opposed to the adrenal cortex. Okay. Hopefully this is a little bit of review for you in terms of how the adrenal medulla operates. The adrenal medulla is innervated by the autonomic nervous system, and in particular, notice this label, preganglionic neuron, okay? So ordinarily in your autonomic nervous system, you have a preganglionic neuron, you have a ganglion, you have a postganglionic neuron, which can be short or long, depending upon whether you're talking about the parasympathetic or sympathetic nervous system. And then from the postganglionic nerve fiber, you get secretion of norepinephrine, okay? In the case of the adrenal medulla, it's a lot like that. This preganglionic neuron synapses directly onto the adrenal medulla, okay? So instead of synapsing onto a postganglionic neuron like you would get in a ganglion, you get synapse directly onto the adrenal medulla, and then the adrenal medulla, in response, secretes granules, just like your postganglionic neuron would secrete norepinephrine. Your adrenal medulla secretes epinephrine primarily, with a little bit of norepinephrine. There's some ATP there, some neuropeptides, but what I want you to be mostly aware of is the epinephrine, okay? And it secretes it into the bloodstream where it can be used as a hormone, okay? So the way that you can think about this, and this is literally the way that I think about it, the adrenal medulla is one big postganglionic neuron. And that one big postganglionic neuron secretes epinephrine instead of norepinephrine, and it secretes it directly into the bloodstream instead of directly onto a target organ, okay? So that's pretty much the way that it works. So the adrenal medulla controlled by your autonomic nervous system in the same way, you know, norepinephrine release is from nerve endings is controlled, okay? All right. So some general characteristics. First of all, released from chromaffin cells in the adrenal medulla. It is stimulated by the sympathetic preganglionic neurons, just as I told you a minute ago, okay? Most of the transport is in solution, unlike the steroid hormones, which sort of need a plasma protein to bind to them because they're hydrophobic. These hormones are nice and hydrophilic, and they are soluble in blood. It binds to beta-adrenergic receptors, just like you learned in the vital fluids block. And it has many of the same effects that you learned for norepinephrine in the vital fluids block, okay? A very variable, you know, number of responses. Basically, it does everything your sympathetic nervous system does, okay? So we aren't going to cover all those again, but I'm sure you guys are aware of them. You should know them ad nauseum by now. I expect you to remember them, okay? All right. So what does all this have to do with glucose? Again, a reminder of what we're dealing with here. Blood glucose, plasma glucose is your regulated variable. Your body does what it can to keep that blood glucose within a normal range, okay? If it drops too low, it releases those hormones that we've talked about, and then I'm going to show you again in a minute. And if it gets too high, then you get insulin release, and that brings it back down, all right? So you're regulating plasma glucose level. All right, these are some of the effects of these are some of the conditions that stimulate the release of catecholamines. None of these should be a great surprise to you. Illness or trauma or stress, hemorrhage, exercise, hypoxia, anything that you think might stimulate a sympathetic response is going to stimulate the release of catecholamines by the adrenal. Exposure to cold, this is a response of your hypothalamus to cold. We'll talk about this in more detail in your second year, okay? But the one to note, of course, for the purposes of this section of the curriculum, blood glucose. Low blood glucose stimulates the release of catecholamines, and as you might expect, the catecholamines are going to act to bring that blood glucose back up toward normal, okay? Note, again, just as I said, the other thing to notice about these, in general, many of these same conditions are part of, generally they're part of a general increase in stress, okay? And as you will find out later on, cortisol is your major stress hormone. Well, catecholamines are released in response to stress as well, and you're going to find out that they act synergistically in terms of the response to stress. And that shouldn't surprise you, especially in terms of the catecholamines. All of these should make sense in terms of the response of catecholamines to general stress, just in terms of the cardiovascular effects, if nothing else. Okay? All right. So here is our familiar table, and you're going to see this again, so don't, hope you're not too bored with it yet. Again, here is our insulin. Its primary job to bring glucose levels down when glucose levels get too high. Here are our 4 other hormones, and their primary job in general is to bring substrate levels up when they get too low. Okay, in this case we're talking primarily about glucose. Okay, a nice redundant system here. Insulin is the only one that brings glucose down. Okay, and we are going to talk specifically about epinephrine here, our primary catecholamine from the adrenal medulla. And what you're going to see is what epinephrine does, generally speaking, is going to make sense to you in terms of bringing substrate levels back up toward normal. So epinephrine is going to be released generally, or at least one of the reasons it gets released, is in response to low substrate levels, low glucose levels in the plasma. So an increase in glycogenolysis will increase your glucose, bring your glucose levels back up toward normal in the plasma. An increase in gluconeogenesis will increase glucose levels and generally bring your glucose levels back up in the plasma. Blocking glucose uptake in the tissues will prevent the glucose from decreasing and will help maintain glucose levels, bearing in mind that the tissues that need glucose will get what they need, okay, despite this blockage of glucose uptake. And blood glucose levels will increase, and that's the purpose. We have an increase in lipolysis and an increase in free fatty acids in the blood, again, meant to bring substrate levels up in the blood so that there's plenty there to supply the tissues that need it. We have no effect on proteolysis in contrast to cortisol, which actually increases it. There's no effect here and no effect on amino acids, okay? So nothing in terms of the proteolysis, but certainly the effects on fatty acids and the effect on glucose and these, all these reactions that regulate those should make sense to you in terms of epinephrine's general response to a decrease in plasma substrate, a decrease in blood glucose, okay? So here we have the actions of catecholamines. Of course, the breakdown of glycogen to increase blood glucose and bring blood glucose back up toward normal. That makes sense. We have an increase in lipolysis, more free fatty acids and more keto acids in response to that. That should make some sense to you. An increase in substrate levels. Note the blockage of glucose uptake by decreasing the effect of insulin on the peripheral tissues. And of course, we also have a decrease in insulin release and an increase in release of glucagon, another hormone that you're going to be learning about. This will reinforce the effect of glucagon upon the system, which is going to raise blood glucose levels up. So glucagon, another hormone that is released in response to low blood glucose, and its primary purpose is to bring glucose up. You'll hear about that a lot more from the biochemists. So we are reinforcing the effects of glucagon, and we are blocking the release of insulin and blocking the effects of insulin. Both of these targeted toward raising glucose levels back up toward normal, okay? All right, that's all I've got. Thank you for your attention.